Recording is rolling. So it is Thursday, October 13th. Now, you guys remember yesterday was a weird day. That was a PSAT day. I didn't have classes most of the day. But I did set you guys up with O'Neill cylinder panel. You guys remember that? O'Neill cylinder panel? Right, so you guys made a margin on the right side. Right, so if you did finish that, looks like some of you guys did and turned it into the gray bin already, that gray tray. So turn that in and I will glue that together. So here's a pretty good example from earlier. Yeah, this is Megan Henry here. So see how it's like an aerial view? Now, if you did do aerial view, that's okay. So it's just like use your imagination type thing. But I got a margin on the right side, and then got another panel right here. I can just glue these. And look at that. Ooh, look at that artistry. Oh yeah. All right, so then we're gonna loop that around to the circle and hang that from the ceiling. Courses quiz. Hey, oh yeah. If you're here, so you got the paper? Yeah. All right, so if anybody doesn't have the paper, give me one right here. Yeah, you can just turn that to gray tray by tomorrow, and then I will put that into the O'Neill cylinder. All right, courses quiz. So this was one of the last grades that went into quarter one. Now, here's how this is working. The first few quizzes, I'll let you guys do corrections if you wanted to. So I'll let you guys do corrections, but you have to staple your quiz to your corrections when you turn it in. Here's why. So quarter one grades, I don't have access to at all. It's never been that way in the past. In the past, I've always been able to see, see how you guys did on blah, blah, blah assignment from previous quarters. Okay, this quarter, I can't even access that data. So I have no idea who got what grade on any assignment. All I can see is your overall grade. If there's a way to access that, I don't know. I think they changed the system, or they must have. So suppose you got like a 73 on the quiz. You can write corrections. Remember, if it was a problem you solved, you can write out the equation and solve it. If it was a graph question, you can just draw, break out a ruler, draw some axes, label the axes, and draw the correct graph. If it was a conceptual question, then you can just write the sentence that is the correct answer. But then staple that to your original quiz so that I can see, oh yeah, here's what you got in the original quiz, and I'll put in the points. So the points obviously are going to go on quarter two, but that'll be all right. So I'll even it out. Okay. Homework page for honors. All right. Since you guys are honors sitting in front of me now, for my conceptual classes, you guys have something a little different going on. But for my honors classes, you guys know I gave you guys chapter 7 gravitation. Okay. I forget. Or anyway, both sides are chapter 7, and what I assigned to you guys are some problems from chapter 6 and some problems from chapter 7. Okay. Now we haven't quite got to this yet. I still need to go over these with you guys. But you may have been noticing, like, where are the chapter 6 questions? So, oops, I did not put those out. I had posted these to Google Classroom, so these have been on Google Classroom along with these for a good while now. Okay. I was going to print these off this morning, but all the printers were broken on campus. So hang tight on that. I will eventually print this page out and give it to you guys. But if you want to see what these questions are, these are all centripetal force related questions. Okay? Then that page is on Google Classroom. So that's there. I'm going to print that out, give that to you guys, and eventually, of course, I'll solve those with you guys. Tomorrow, there's a pep rally. So you're not going to have a 7th period tomorrow. It's going to kind of throw off all my classes. So I'm going to teach you guys as much about universal gravitation and orbits as I can today. We'll get as far as we can. Tomorrow I'll have something lined up that'll be worth your time to come to class. You guys will get to learn something, but we're going to have to pause the stuff that we do today until Monday. All right, so let's get going on universal gravitation. So let's do kind of historically chronological. I'm going to switch my screen over, and we're going to take a trip through time. Here we go. Okay. So suppose it's like thousands of years ago, and you're looking up at the sky at night. I mean, what can you really do at night? Not very much. I mean, you can't read a book or watch internet videos, but you can look at the sky. In fact, people were so tuned into the sky back thousands of years ago, they could read the stars like you guys can read a book. Like you open a book. Here, guys. Here, you see some words. You immediately know what those words mean. You can make sense of it, right? If it was like 5,000 years ago, right, and we all stepped outside and looked at the sky, we could say, oh yeah, it's definitely October because that's where those stars are, blah blah blah, this season of the year, right? And then now what it looks like from our perspective is it looks like the stars are going around us, and that was people's natural assumption is that here's the Earth at the middle, right? And all the here's the sun like going around the Earth, and the planets going around the Earth, right? Everything's like going around the Earth, right? Now you guys possibly have never seen this before, which would be good because this is not a model that we understand to be the truth today, right? But this is what people understood for a long time. But if you watch the motion of the planets very carefully, here's Mars. You guys see the orbit of Mars right here? Watch this. What was that? What was that? See, it looks like it makes this weird loop-de-loo in the sky. So from the perspective of Earth, it looks like, yeah, Mars is going around us. And then it appears to have this retrograde motion where it goes backwards in the sky and then continues forward. Okay. By the way, the word planet, do you guys know what language the word planet comes from? Planet, what language does that come from?
I don't know.
Greek. Yeah, it is Greek. It's Greek. Right. And do you guys know how it translates, what that means in Greek?
Plane, I believe, is a realm of existence.
It means wanderer. It means wanderer. That's what it means. So if you're looking at all the stars in that sky, since the stars are so far away, they appear to be moving relative to each other. Or, well, they appear to be locked in place relative to each other, like all moving together compared to Earth, right? Okay. But not the planets, right? The planets look like bright stars at a glance, but if you watch them, like Venus or Mars, they look like they're moving independently of the rest of the stars. In fact, they have like these orbital shapes. Right? And so back to here. There's this Greek guy named Ptolemy who came up with this model to include the retrograde type motion. He said, okay, well, we can describe it mathematically, and we can use that to predict the motion of the planets, like exactly the position in the night sky for months, years to come. Right? And his model worked mathematically, right? So you could say like, where's Mars going to be like 5 years from now? Well, let's break out Ptolemy's model, and it does go through these weird retrogrades, blah blah blah. But there was no explanation for why. Like, why if Earth is sitting in the center, why do these other planets do this weird loopy-loop motion? Right? Well, hundreds of years later, along comes a guy named Copernicus, and Copernicus says, "Well, hang on a minute. If you just put the sun at the center, this is called a heliocentric model, right? Heliocentric, sun-centered, right? And have all the planets going around. Here's Earth. Earth is just one of many planets. Right? Then that greatly simplifies the model because now you don't have to build in this weird loop-de-loo retrograde motion that we don't have a good explanation for. Now everything's just kind of going around, right? And that's a much simpler model. And that's the one you guys almost certainly learned in elementary school. Sun's at the center and everything just goes around that. Okay, so that's all fine and good. Until you make extremely precise measurements of location of planets in the sky, for example, Mars. Now, this is what a guy named Tycho Brahe did. He would map where exactly is Mars night by night for years. And then along came a guy named Kepler and got hold of his data and was trying to come up with a really good model for motion of planets around the stars. And here, you guys know what 1 degree is, right? 1 degree is like one tiny, tiny little sliver. Right? If you take a tiny, tiny fraction of that degree, right? Imagine putting this protractor matching up to the sky, right? Saying where is Mars in the sky, right? And saying, well, let's start assuming it's a circular orbit, right? Because that would probably be a pretty good assumption. It's probably pretty close to circular orbit, right? In fact, it's not too far off, but it's not exactly a circular orbit. And the difference this guy figured out was only by like a tiny fraction of a degree difference of where Mars should have been compared to where it was. Like, it's not exactly a circular orbit. What he figured out after some time is that planets don't actually move in circles around the sun. They actually move in what shape do you think?
Oval.
Yeah, like an oval type shape. There's kind of a technical term for it. It starts with an E, called an ellipse. An ellipse. Yeah. Do you guys possibly learn about ellipses in a math class? Maybe algebra 2, possibly? Right, ellipses? Well, I'll teach you guys some stuff about ellipses right now. So I gave you guys some string. You guys got some string on your desk? Right. Now, you might possibly have one from a previous past period that's already tied into a loop. So if yours is not already tied into a loop, then go ahead and do that right now. Okay, tie this into a loop. Okay, bam. There you go. Got a nice loop. Go ahead and double knot that while you guys are finished tying yours. Okay. And maybe for a good measure, I will chop off this excess right here. right, so I got myself a loop. I throw that down on the paper. Right, now you need 3 pencils or 3 pens. Bam, bam, bam. How about that? Okay, so you guys got your loop, right? It's about that size. It's a pretty good size right there. Okay, I'm going to throw down 2 dots on the paper. Okay, you guys see 2 dots? Okay, I'm going to leave these pens fixed in place. Okay. So these 2 pens don't move. Replace this guy with this guy. How about that? All right, those aren't going to move. Right. And then my 3rd pen, I'm going to make a triangle shape. You guys see a triangle? Okay, you guys are doing the same thing? You guys got a triangle too? Yeah, okay. If you don't have 3, then I guess you could just watch and try to figure this out. Okay. This is how you would do this. Okay. Then, okay, well, I could make that triangle, or I could make this triangle, or I could make this triangle, or this triangle, or this triangle, right? Could you go all the way around and create all these different triangles with a string? Okay. And then, ooh, look what we're getting. We're getting, it's back up here. Look at that nice curved line of all the 3rd points, possible points with the triangle. Look at that. Okay. Oh, what's the name of that shape? And it's not a circle. It's an ellipse. Ah, that right there is an ellipse. Okay. But hey, what if I took these 2 pens and I just moved them onto the same point, so they were just a single point? That would have created a perfect circle, right? Okay. So it turns out that a circle is a special kind of ellipse. Similar idea to how a square is a special kind of rectangle. Okay, get to that. Now, to tie this back to physics, how this works out is that the star, like the sun, for example, could be at one focal point. These are called focal points, right? These are plural is foci. Right? So here's a focal point. Here's the other focal point. Right? Bam, bam. Right? Right. The star will be at one of those, and then the planet will follow this ellipse all the way around. Okay. Now, anything that's orbiting, I guess it technically could be a circle, but there's a reason that you don't naturally see circles, and I'll bring that up later in class. Right? Why you don't see circular orbits? Right? But ellipses you see. Right? And then here, let's talk about ellipses a little bit. I want to talk about the math of this. Okay. So here's the center of the ellipse. Bam, that's the center of the ellipse. Okay. I've got this long arm and this short arm. I'll call that A and B. How about that? Right, A and B. See, B is a little bit longer than A. Right, kind of analogous to radius. Right. Ooh, I could make a rectangle with this. Can I see a big old rectangle? Right. Wouldn't the area of that rectangle be A times B? Would that be true? Okay. Now, question for you guys. And some students, some classes have figured this out today. What if you guys are going to be one of these classes to figure this out? Okay. See the area of that rectangle and the area of that ellipse, right? How many of these rectangles do you think you could fit in this ellipse? Another way to say that is, what is the ratio of the area of the ellipse to the rectangle? How many rectangles do you think could fit in this ellipse?
3.14.
Bam! All right, you guys are winning class right here. Right. Caleb got it, 3.14. Right? That look about right? A little bit more than 3, maybe 3, a little more than 3. Right, so it turns out that the area of an ellipse is equal to pi times A times B. Pi AB. Right? 3.14 of those rectangles. There you go. Okay. Back to tie us back to a circle. For a circle, A is equal to B, isn't it? Right? And so the area would be pi r squared. Right? But you guys know that already. Okay. Another question for you guys. One trip all the way around the ellipse. That would be called the perimeter, right? The perimeter of an ellipse. Does anybody know the equation for the perimeter of an ellipse? Does anybody know that? The answer is no. Nobody knows. Okay? This is a mathematical mystery. There may have possibly been an approximation in one of your math textbooks. I don't know. But the true answer is nobody really knows. Okay? So, what is the perimeter of an ellipse? How far is it all the way around an ellipse? Okay? Like for a circle, it's 2 pi r, right? If this was a perfect circle, it would just be 2 pi r, right? But an ellipse, there's some approximations, but nobody knows. Okay. So Kepler had these 3 laws of planetary motion. Right? This is one of the new posters that's hanging above my head right here on the ceiling. Okay, guys, 3 laws of planetary motion. So these are Kepler's laws. Now Kepler predates Newton. That's why I'm actually starting with Kepler, just chronologically in history. Okay? And his first law of planetary motion is that planets actually move in ellipses around their parent stars, so like around the sun, right? With the sun at one focal point. Okay? Now he was again mapping this motion, saying what else can I figure about this out about this motion, and he figured out well what became the second law. So let me guide you guys through that. Now, as this planet's going around, okay, the fact that sometimes it's a little bit closer to the sun and sometimes it's further away. Do you think the planet's speed is going to change? Its tangential speed. Sometimes it's going a little faster, sometimes a little slower. Okay. What do you think it's doing on this side of the ellipse, where it's really close to the star? Really fast or really slow? How many of you guys think really fast it's swinging by? You guys think? Yeah, really fast. So like in 1 month, maybe it might go from here to here. Like the planet's there, and then the planet's there, like 1 month later. Right? Okay, so let's be going relatively slower on the other side, right? When we get to conservation of energy, we'll probably revisit this idea too, because it's a really good example of that. Okay. So in 1 month, maybe it goes from about here to about here, right? So the fact that its tangential speed is slower, it's not going as far during the same time period, right? Really fast, really slow. Okay. And what Kepler noticed is that if you make this wedge like a pizza slice, okay, you guys see that pizza slice looking wedge right there? Okay. And then you do that over here. Okay. Remember, these are for the same time period, right? Do you guys think that that area looks approximately equal to that area? In fact, Kepler said that would be exactly true for exactly the same time periods. So sometimes the second law of planetary motion is called equal areas and equal times. Those 2 green wedges. There's the same time period. It's the same area. Okay? It's crazy he was able to figure out any of this stuff. But this one, maybe a particular reason I could say this was crazy to figure this out, because this seems like a really complicated integral calculus type question. And this was before Newton, so this is before calculus has even been put down to paper yet, that you figure this out. Okay. Then many years later, Kepler was able to formulate another law of planetary motion, his third law of planetary motion, which relates to the time period, let's say how much time does it take to go around, to the average distance to the star. Now, of course, the distance changes because these are elliptical shapes, but maybe like an average distance, maybe like the average of A and B, right? There's like some, I mean, these ellipses are pretty close to circles, right? For planets, they are anyway, right? So if you get further away from the star, then it takes more time to go around, obviously, right? But this ends up being the proportional relationship. So the cube of the distance and the square of the time period are proportional to each other, directly proportional. So for example, if you went twice as far away, right, if you doubled the r, see, 2 cubed is 8, right, and then take the square root of 8. What is the square root of 8? That's like 2.8, right? So again, if you were twice as far away, 2 cubed, take the square root, it would take you 2.8 times the amount of time to go around. Okay, you guys got that? Okay. And then anything that's orbiting this the sun has to go in this elliptical shape. Comets have elliptical paths that are extremely elongated, right? They're so elongated when they're passing by the sun, they're really close to escape speed, but not quite, because they have to like stay in orbit. We'll actually talk about escape speed. If you went so fast that you could actually break the gravity and fly away, you would actually be on a hyperbolic path. There was an object a few years ago that flew through our solar system that came from outside our solar system. They called it Oumuamua, and it followed a hyperbolic shape path. Right. All right, so that's all fun. Let's move on to this poster here. So you guys see this hanging on the ceiling. So we're going to move ahead in time to Isaac Newton. Along comes Isaac Newton. Right. So Isaac Newton knows about Kepler's laws of planetary motion, and he goes home in 1666 and works out laws of motion and mathematics, and lays down calculus, blah, 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 right? At some point, oh yeah, go ahead. Yeah, go ahead. At some point, he sees this apple fall from his tree, and he starts thinking about that. And he looks up and he sees the moon. And Newton is the first person in history to make the connection that the apple falling from the tree and the moon going around the earth are part of the same phenomenon, part of the same laws of physics. And here's his reasoning. remember, Isaac Newton comes up with laws of motion, law of inertia, force equals mass times acceleration, whole deal. So Isaac Newton knows that anything that's on a curved path must be subject to a force called a centripetal force, right? There must be a force that's causing it to be on a curved path. Well, the moon is on a curved path. The moon is orbiting the Earth. So what is that force? Oh, well, it must be a gravity force from the Earth, just like the Earth is pulling down on the apple, right? First person figured that out. Right? By the way, that's where we're eventually headed with the story. Is we're gonna take this universal gravitation, which I'm starting to feed you guys. Right? We're gonna combine it with this centripetal force and create orbits. Like what's the orbital speed? So by the end of class today, we'll be there. Okay. So I'm gonna basically copy this onto a blank page, okay, and then this is like the end result, right? But step by step, so one step at a time here. Okay? Suppose you have two objects floating around in space. This might be two asteroids. This might be the Earth and the Moon. So two objects, and I need to give them masses. So I'll call this guy capital M, and I'll call this guy lowercase m. Some textbooks do M sub 1 and M sub 2. I've always done this. I'm just going to stick to that convention. And there's some distance between the two, some center to center distance. Right? So I'm going to treat these as point masses, as if their entire mass individually was located right at the center. Okay? And the distance between them, I could say d or x. I'm going to call it r. And the reason I'm calling it r is because r could stand for like radius, like radial distance. Right? If this was the Earth and this was the moon, could the moon be in orbit around the Earth? With some radius of orbit, right? Radius, right? Which sure does remind me a lot of your guys' last lab, right? It looks a lot like that motion, right? Earth, moon, there's a force. That's where this is all sort of heading. Okay? Now, the Earth pulls on the moon with a force, so I'll go ahead and draw that force. Label it F for force. Right? Guys, does the moon pull back on the Earth? Yeah. That's one reason. Like, what we have tides. That's evidence of that. Okay. But which force is bigger, the Earth pulling the moon or the moon pulling the Earth? The same. Same force. I can't trick you guys. Same force. Same force. That's Newton's third law of motion, right? This force is this force. They're the same force. Right? You guys know that. Same force. Right. Now, how can we come up with a formula for this force? Okay. Well, I'm going to create a fraction. You guys need the answer hanging from the ceiling, but piece this together. Right? Suppose we're with Isaac Newton back in the 17th century. We're trying to piece together this idea. Okay. Hey, do you guys think that the more massive one of these objects is going to create more gravity force? Right. In fact, that should be a direct proportion. Right. It's like if you double this mass, probably double the force. If you double this mass, probably double the force. If you double both, double. Do you think you'll get 4 times the force? Okay. So I'm going to say that this force is proportional to each mass and multiply those two together. Okay. Now, this gravity force between them also has something to do with the distance between them, right? So what if these objects were further away from each other? Do you think the gravity force would be stronger or weaker? It have to be weaker, right? For larger distances. If they're really close, yeah, huge gravity force. If they're really far away, smaller and smaller gravity force. Right. So I'm going to put that distance r somewhere in the denominator, right? But it's not just r. I mean, you guys see the answer is going to be r squared. Like, why is that? So let me flip over here, and I'm going to have Paul Hewitt explain why it's 1 over the distance squared.
Let's suppose I have here a candle flame, and that candle flame shooting light out, sending light out equally in all directions. Except straight down, the candle's in the way. But anyway, the influence of the light goes off in all directions. You will find when you study light that the intensity of light varies as the inverse square of distance. You will find when you study radioactivity that the radioactiveness varies as 1 over the distance square. You will find out magnetism with a magnetic pole here, that the magnetic field strength goes off as 1 over the distance square.
No, magnetism. I'm not sure that's actually true. I've seen other stuff, but anyway, his general idea is true for light and also for gravity, right? Now why is that? That's 1 over the distance squared. It has to do with the fact that we live in a universe that has 3 spatial dimensions, right? That's a hint what you guys are about to see, right? 3 dimensions.
You will find out when you talk about electricity and you've got a charged object here, that the further and further away you get, the electrical influence peters off as 1 over the distance square. All through physics, you'll see something over the distance square. And I want you to see that that's intuitive. We'll do it now for the case of light. Let's suppose this eraser is a piece of photographic film, and I hold that photographic film right here. There it is, okay? I'm catching light. In fact, the shadow's cast, isn't it? I'm catching all the light that comes in here and out to here. I can't draw this part out here, okay? But that's how much light I'm catching. And let's say I'm a particular distance away, and I'll call that distance to there. Okay. The question is, if I get twice as far away, will I catch less light or more light? Because if I hold it here and I bring it into the darkroom and develop it, the film there is going to be darkened there, isn't it, with a light hit? How about if I held the film twice as far away? Twice the distance. It's about here. Oh, look at this. Out here. This could fit in the shadow. I could get 2 erasers in the shadow. Could I get 2 erasers in the shadow or more? In the shadow cast by this. Some people say, oh, 2. I can see 2. 1 here and 1 there, and that's the end of it. And other people say, no, 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 no. You get more than 2. More than 2 erasers will fill the shadow. See if your neighbor knows. Begin with F, end with or. 4. Excellent. All right. You could get 1 here, 1, and out like this too, see? It's sort of like that, like 3D. So you know what? 1 eraser here would catch 1/4 as much light as if it were here. Do you see that? 1/4 as much because the rest is going here, here, here. So 1/4. Let's suppose I get 3 times as far away. That's about out to here. Out to here, that about right? 1, 2. I'm not sure if it's drawn a scale again, but over here I get, look, 1, 2, 3. I can get 3 erasers. So someone say, gee, 3 times as far away, 1/3 the light. Because this would get 1/3, the rest would go up here. 1/3 is wrong. What's the answer again? Neighbor. It's a 9th, ain't it? Huh? So you get like this. See that? See this eraser? Here it is over here. It's only getting 1/9 the action because the rest is all coming out here. And so then I could say, what if I put it 10 times as far away? And you guys would say, hey, it's not catching 1/10 the light, it's catching 1 what? 100th the light. Because 10 times as far away, I could have 100 erasers fill up the shadow that this one took. 100 erasers would be required to catch all the light that this one here caught. So the intensity out there would be 100th. Guess what behaves the same way, gang? Begin with a G. Gravity.
Gravity. So let's flip back over here. All right, and finish this equation off. Right, so you guys saw inverse square relationship between the distance and the gravity force. So go ahead and put that down here. I've been using R, so you gotta stick with that. Okay. Now, one more thing to tie this all together. This isn't quite finished yet. Now, it's okay. I could say proportional too. That would be R. Okay. But kilograms, meters squared. Isn't this kilograms squared over meter squared? Which doesn't sound like newtons, which would describe a force. So the units don't quite match up. So I need some kind of constant to tie everything together, not just in terms of units, but to make it an exact number too. So number of units. And that constant is going to be capital G. Okay. So capital G stands for the universal gravity constant. Okay. Okay. Is that okay so far? Okay. And that universal gravity constant. Right there. Give it to you guys. G equals goes like this: 0.667 Newton meter squared per kilogram squared. Okay. Or some textbooks put in strictly base SI units instead of newtons. They'll have like strictly kilogram meters in seconds, but I always see it that way, so I'll do that. Okay. Oh, that's an extremely tiny number, isn't it? Okay. Which kind of makes sense. Think about it. Right? That gravity would have to be because gravity is a pretty small force. Like there's a gravitational attraction between any 2 objects in this room, but you don't really feel that, right? It's not like you get closer to something and then suddenly you notice it tugging on you. Right? It's such a tiny value. The only reason you have like a significant weight that you like, can appreciate is that the mass of the Earth is so huge, okay, which we're kind of getting towards, but it's like that, right? Now, how many guys are looking at that big old string of zeros there thinking, huh, there's probably a much more efficient way to write that number and to type it into your calculator. Okay. What are you guys thinking? Do you guys remember scientific notation, right? Can you guys write that in scientific notation? Be 6.67 times, right. How many decimal places from here to here? Is that 11 places, I think? 11, right? So can you guys finish this before I do? So it's 11 places over. Did you guys just write 10 to the negative 11 Newton meter squared per kilogram squared? That's what you guys just wrote, right? Okay. Because remember, negative exponents, that doesn't make the number negative. That makes the number small, right? That says we're dividing by 10, and then you do that 11 times. Okay, guess what? See, if it was like 10 to the 11, the decimal would be going the other way. It'd be a huge number. No, it's a really tiny, tiny number. Right? All right. So you guys got that. Let me throw a little bit different model at you guys. But we're gonna come back to that. Right. You guys know the gravity force of attraction between two objects now is gmm over r squared. Right? Mass multiplied by distance squared multiplied by universal gravity constant. Okay. Let me do the same thing, but I'm going to modify the model a little bit. Okay. What if one object is the Earth, right? I'll do that capital M. Okay. And the other object could be you. Let's say you have a mass, right? So mass M. Okay. Now, what is the distance between you and the Earth? You might think, well, 0. I'm on the Earth, right? But from a universal point of view, we're treating the entire mass of the Earth at its own center mass and your mass at your own center mass. And the distance between those two values is the radius of the Earth. This is, I'm going to use capital R for like a fixed radial distance. So I'm trying to stick to convention of lowercase r could be like in general, and capital R could be like the fixed radius of a planet, for example. Okay. Right. So that is the distance between you and the Earth. Oh, well, this is going to explain where your weight comes from, because isn't your weight a gravity force? Force due to gravity? That's that, right? Universal gravity constant times the mass of the Earth times your mass divided by the radius of the planet squared. Wouldn't that be true? Right. Now, each of you has an individual unique mass and also an individual unique weight. Right? But there is something that's in common for all of us, and isn't that the gravity field? Right? Like if we all jumped, then wouldn't you all be accelerating downward, right? Free fall, right? Right. And that number should be the same. We've been through this before, right? Different objects have different masses and also different resulting weights, but the ratio of force to mass is the same, right? Isn't that what free fall gravity is? It's weight divided by mass, right? And that's the same for all objects at the surface of the Earth, right? And what number is that? Like 9.8 meters per second squared, right? Guess what? Okay, so if I take this expression and I just divide out this unique mass, wouldn't that give me the gravity field at the surface of Earth is gm over r squared, or really any planet? This could be general for any planet. Gravity field, wouldn't that be true? Okay. So now you can figure out what is the gravity field at the surface of any planet if you know the mass of the planet and the radial size of the planet. You see that? Okay. So pop, just pop it in there like that. Okay. All right. Now here's where okay. I might do some of this stuff where you get with guys where I care about proportionals. Like what if you double the mass of the planet? Right? If you double the mass of the planet, but you leave the radial size the same, you guys see how the gravity field will also double? What if you double the radial size of the planet, but you left the mass the same? Maybe you have like a huge styrofoam puff planet. Right. See, if you double that, guys, what's 2 squared? 4. 1 over that. 1 over 4. Hey, wouldn't you have like a quarter of the original free fall gravity? Right? If you double the size of the planet but left the mass the same, like a giant puff planet, right? Or what if you do both? What if you double the radial size and you use like the same dirt, like right? So the mass increases at the same time. Okay. Now here's where we're gonna get in. Right, go off a little bit of tangent with you guys, but let me see if I can dig up these notes. because I'm throwing some stuff at you guys. You guys are pretty sharp that I did with my AP classes this morning. Okay, where is it? Ah, it's this page right here. Okay. This is eventually going to come back in spring semester where we talk about the scaling. You guys see this big old cube? Right. This big crate compared to this little box. Right. So the big crate has 3 times the length, right? But also 3 times the height, 3 times the depth, right? Okay. Okay. So do you guys see how the volume of the big crate is 27 times the volume of the little box? Okay. So when you scale something up, different properties change in different proportions, right? Anything to do with the length, or like if you walk around it, would in the picture look at here would scale it by a factor of 3. Surface area would scale it by a factor of 3 squared, right? Which would be 9 times. And the volumes scales up by 3 cubed because 3 dimensions, right? 3 times 3 times 3 is 27. You guys see you can fit 27 little boxes in the giant crate. Okay. All right. But maybe keep that idea in your back pocket. We might come back to that later. Okay. But for today, just for now, let's more simply just plug in numbers and see if this all works out. Okay, so gravity field, we have an expression for that. So let's go back to this. I'm going to give you guys the mass of the Earth, which is 5.97 times 10 to the power of 24 kilograms. Woo! Okay, here's 1 kilogram. So if you had 1 followed by 24 zeros of these, you can be getting pretty close to the mass of the Earth. Here's the radius of the Earth. 6,371,000 about meters. Okay. Oh, side note here, I need to do a long overdue correction. Okay, let's go back to one of the very first days that you were in this class. Remember I was telling you guys about metric system? Okay. Does anybody remember where 1 meter length comes from? Like, what was the original definition back in the 1790s? Right. What 1 meter? What's that based on? Something to do with the size of the
It
Earth?
was based off of the gravitational field. I don't remember exactly how much it was, but I think it was like 10,000.
Ah, yeah, 10,000 kilometers is what it ends up being. Right. So if you go from the North Pole down to the equator, that is 10,000 kilometers or 10 million meters. Right. I think back in the day I said 10 billion. And if I did, then oops, sorry about that. It's 10 million. That's what it is. It's 10 million meters, right? Which is exactly consistent with this radius right here being 6.37 million meters. Right. So there you go. If you want to check my math on that, can. Right. That's a quarter circumference of circle. All right, but we're gonna go plug in and chug into gravity field is equal to G M on R squared. Okay. Let's do this for the Earth. Gravity field of Earth is equal to, I'm going to set the big old fraction. Okay. Now, what I'm about to do, you guys got calculators on your desk? Okay, follow along with me. This is really good practice because something I've seen over the years of teaching is a lot of students struggle typing numbers into calculators when there's going to be parentheses involved, there's scientific notation, there's going to be numbers that are squared, there's fractions, right? So, yeah, so you can get some practice along with me. And if you type everything into calculator correctly, like I do, then you know how to use a calculator. So G, 6.67 times 10 to the negative 11. Okay. You know what on G2? All these numbers have units on them. I'm going to pull the units out to the side. You guys know this is going to be some meters per second squared in the end, right? Describe a gravity field. Or it could be newtons per kilogram. That's the same thing. Okay, but here's the numbers. Mass of the Earth, 5.97 times 10 to the 24, of course that's kilograms. And then radius of the Earth being squared, 6.37 times 10 to the 6. That's being squared, right? Okay. All right, calculator time. Okay. See if you guys can get this when I do. Open parenthesis, 6.67 times 10 to the power of negative 11. Here's one of the summing blocks already. You guys see there's 2 minus signs on your calculator. They mean different things. The one on the right means subtract. Don't do that one. The one on the bottom means make a number negative. That's the one you have to punch. Right? If you do the wrong one, then the calculator is going to blow up, a little tiny fireball. But got that. I'm going to close parenthesis, open parenthesis. 5.97 times 10 to the power of 24. Close parenthesis. Divide by open parenthesis, 6.37 times 10 to the power 6, close parentheses square. Okay, that's one way to do it. Okay, and even before I hit enter, I already know what number is going to pop up on my screen. Okay, did you guys already do it yourselves? Okay. And what number is showing on your calculator? 9.8. Good call. It is 9.8. Okay. You know what? If I have 3 sig figs, and it looks like I do, maybe I could even say 9.81. That'd be meters per second squared. Okay. Now this value varies depending on where you're standing on Earth for a few different reasons. So I've seen anywhere from 9.79 to 9.82 be cited for Earth gravity. Okay. 9.8. There you go. Meters per second squared. All right. So pretty good, right? All right, so we got that. All right, that's the gravity field, surface of Earth. Now let's talk about Newton's cannon. Newton's cannon. I get these pages sorted. So Newton was watching the apple fall and looking up at the moon and saying, "Hey, I want to tie these ideas together. What if I had a crazy tall mountain that was so tall it went above the atmosphere, which actually the atmosphere in proportion to the radial size of the Earth is not that big. I've heard like if the Earth was the size of a basketball, you take that plastic wrap that you could wrap stuff up, really tiny, thin plastic wrap, and wrap that around the basketball. That'd be a pretty good approximation for how thick our atmosphere is compared to the size of the Earth, which is not that much, right? Okay. Right, so like this mountain would clearly be big enough, right? Okay, you perch a cannon on top of this cliff that's above the atmosphere, okay? And fire a cannonball, right? Some tangential speed, I will designate V, okay? Now, will that cannonball have a force acting on it? Yeah, its own weight. In fact, its own weight here, just above the atmosphere, which about 400 kilometers up is what you need to reach low Earth orbit. That's where the International Space Station is going. About 400 kilometers up. Okay, it's very small compared to the 6 million meters of Earth radius. Right, so it's not a whole lot different. Okay, it's got a gravity force acting on it right here. I'll do F sub G, gravity force, which you guys know is GMM over R squared. Okay? Mass of the Earth, mass of the cannonball. Okay, so yeah, there is a net force on it, and it's always falling, right? But it's falling around the curvature of the Earth so that it doesn't actually get any closer. And Newton was trying to figure out, well, how fast would that have to be? So for we're tying this universal gravitation right, back to your guys' last lab. All right. Lost track of your last lab paper. You guys remember you had the Plato canisters and the wheelie thing? Okay. You guys figured out centripetal force. So for the centripetal force to be provided by the gravity force, wouldn't that be mv squared over r is equal to gmm over r squared, right? As long as you're like low Earth orbit and this radius is pretty much the radius of the Earth. Let's do a little algebra here. One of the r's cancels. The m cancels. The fact that the m cancels means that when I eventually solve for this v, whatever speed you need to keep something in orbit, okay, it's independent of the mass of the object. So if I go out on the International Space Station and I walk outside and go on a spacewalk, and I take this object out and I let it go, it's just going to float next to the space station all the way around because it doesn't matter. It just canceled out. The little m did, right? This v is the orbital speed for a circular orbit. And you guys see that's just the square root of g m over r, right? There you go. That is this right here, orbital speed. Now that's for a circular orbit. See, if you plug in the numbers for Earth, by the way, the orbital Earth, you guys can test this, but you have all these values in your notes from earlier today. It ends up being about 7907 meters per second. You guys can test me on that. Okay. In fact, probably a good thing to do. Make sure you can square root, blah, blah. Okay. All right, so that's for a circular orbit. If you sent a satellite into orbit that was going any slower than that, suppose it was like going 7,800 meters per second, well, that would be too slow. And it's going to eventually spiral down and crash into Earth. Okay. So that's why you don't see planets going around stars in circles. Right? in the natural world. Because maybe there's like a 1 in a trillion shot that you could find something like that. But if there was a planet that was doing that, and then it slowed down for any reason, maybe another planet swings by, throws off its gravity, it's eventually just going to fall into the sun, and we'll never see it, right? But if you speed this up a little bit, suppose you go to 8,000 meters per second, then it'll go into a slightly elliptical shape, which is a much more stable and safe shape, right? And if you speed it up a lot more, keep speeding up, speeding up, speeding up, you can get more and more elongated ellipses until eventually it reaches a hyperbola and flies off into space. That's called escape speed. Hold on to that idea. We're going to come back to that idea in a few weeks, right? Escape speed. But you guys have orbital speed. There's orbital speed. It's in general and specifically for Earth if you plug in the numbers, right? You guys got any questions from today? All right. So I will see you guys tomorrow, and then we're going to continue this specific adventure on Monday. You guys have a great rest of your day.
Bye.